Welcome back to CET3136C. This is Logic Devices Programming, and in this video we're going to discuss Chapter 4, which is Dataflow Style and Combinational Design. The learning objective for this video is that you will be able to create a VHDL architecture using the Dataflow Style Combinational Design, and we're going to go a little bit further by discussing some more of the methodologies we can use beyond just simple Boolean expressions in order to implement a Dataflow style design. And we are going to be focusing on combinational design. As a reminder, combinational logic has no memory. The outputs are only dependent on the present state of the input. So we're just going to be focusing on basic combinational design. So VHDL provides a full set of logical operators. We've already seen a few of those in the previous videos that have been posted, as well as some of your labs that you've already been working on. We can see that there are logical operators already available to us within VHDL. So those include not, and, NAND, or, NOR, XOR, and XNOR. So anytime you want to use any one of those logical operators, you can simply type that keyword into your code and you will be able to perform that operation on your two signals. And depending on what you're doing, it could be two or more signals. So the table on the screen shows you the logical operators that are defined within VHDL. Take a look at the bottom. All operators except not have the same precedence. Not has the highest precedence. So everything has the same precedence, which means without parentheses, everything will be evaluated left to right. Left to right, no precedence between NAND or NOR. The only thing that has precedence is not. So if you are trying to write a statement that has a combination of logical operators, it's going to be evaluated left to right unless you have parentheses in your expression. So here's an example. Let's say that I have a signal C. C is going to be the value of A and not B, or not A and B. If you type your code exactly like this, it's going to be evaluated left to right with not having precedence. So, for example, it'll do A and not B. So first B will be inverted, and then A will be ANDed with B. And then the operation will continue from left to right. So if that's not what you intend when you're writing your code, you must use parentheses to define what you need to happen. So how is this interpreted? This is how it would be interpreted. A and not B, so the not B comes first, then that gets ANDed with A. That result would be ORed with not A, and then that result would be ANDed with B. Let's say that's not what you intended. Maybe this is what you intended. If that's the case, you must put parentheses in order to define what you need to happen. When it comes to arrays, we can perform logical operations on array elements, or we can perform a logical operation on an entire array itself. So for example, let's say I have two signals, X and Y. They are standard logic vector, they are an input, and they both have a size of 3 down to 0. So that means there are 4 elements in this vector, and then there's an output vector F with 4 elements as well. Remember, when we discuss arrays, the size right here determines how large the array is, and it also tells you where the most significant bit is. So in this case, cell number 3 is your most significant bit in this vector, in this array. So within an array, we can do a logic operation on an individual element. Let's say I want to take X3 and AND it with Y3. I can do that and store that in F3. Now I don't have to use cell 3. I could pick any one of the elements within the array, any one of the indices within the array, or I can AND two arrays together. I can say X and Y only if those two arrays are the same size and the same type. So if you try to perform an operation like this and you don't have X and Y defined as the same size and the same type, you will get an error. So whenever we type in this expression, F gets X and Y, here's what happens. The most significant bit in X gets ANDed with the most significant bit in Y. And notice that these are two different indexes. Why does that happen? Take a look at how x and y are defined. X is defined as an input standard logic vector 3 down to 0, which means cell number 3 in that array is the most significant bit. For y, it's an input standard logic vector 0 to 3. So cell 0 is the most significant bit in that vector. So if we were to type in this expression, f gets x and y, it's going to start from the most significant bit of each vector and work down to the least significant bit. It's not going to match the indexes, you know, as in x3 and y3. Nope, it's going to go based on how you define those two vectors in the first place. So watch out for that. Generally, we want to be consistent in how we define our vectors so that as you perform operations later, you don't get things confused. But based on this definition, if I were to perform a logic operation on an entire vector, this is what would happen cell by cell. So these two expressions are the same. So next we're going to do a couple of examples implementing some digital devices in the Dataflow style. The first thing we're going to implement is a 4-to-1 multiplexer. So just to remind you of how a 4-to-1 multiplexer works, we're going to have 4 inputs. We're going to call those inputs C3, C2, C1, and C0. We have our output Y, and then we have selects. We have A, B, and G bar. G bar is going to act as an enable. So when G bar is equal to 0, so that's an active low enable, that's why it's called G bar. When G bar is low, A and B will select 0 to 3, depending on what the values of A and B are. So it has to be enabled by having G bar be low. Otherwise, none of these signals are going to pass. Once it's enabled, the selection of A and B is going to determine which signal will pass to the output. So let's make a truth table to sort of describe this scenario. So here's my truth table describing what's going to happen, assuming that the mux is enabled. So we're going to assume that G bar is low. A and B are going to determine which signal passes to the output. So when A and B are both low, C0 should pass. Logically, using Boolean expressions, that would mean that not A and not B and C0 is going to create the logic expression that will allow C0 to pass through the mux whenever the select inputs are both low, whenever A and B are both low. When A is low and B is 1, C1 should pass. So that means our logic expression or our Boolean expression for the output would be not A and B and C1. That Boolean expression will define the fact that C1 is going to pass through the mux whenever A is a 0 while B is a 1. And then when we reverse that, when A is 1 and B is 0, we're going to get C2 passing to the output. Logically, using a Boolean expression, that means we have A and not B and C2. That's what's going to happen when C2 passes through to the output. And then lastly, if both of these are 1, C3 should pass. So that means that A and B and C3 is the Boolean expression that describes this scenario. So what we're going to do now is go into Quartus and actually write the code for this multiplexer using the Dataflow style, and we're going to start by using basic Boolean expressions using this truth table on the screen. All right, so I'm in Quartus and I have a new project. I've called it mux 4-to-1, and I'm going to start with my context clause. So there's my context clause and my library IEEE statement, my use clause, and then I'm going to start with my entity. I'm going to call it mux 4-to-1. Just like the name of my file. And then I'm going to write my port statement. So to begin, I've got C0, C1, C2, and C3. Those are all inputs and their standard logic. I also have G bar, A, and B. Those are inputs. standard logic. Then I have Y, that's an output, standard logic. There's the end of my entity declaration, and now let's do the architecture. So I know that my output, Y, is going to get a Boolean description of the operation of this multiplexer. And the first thing that has to happen is it has to be enabled. So what I'm going to do is use the logic function AND. And I'm going to take not G bar and AND it with what's supposed to happen according to the selects A and B. So if G bar is not a 0, it doesn't really matter what happens after this. It's not going to be enabled and we're not going to have an output. So we're going to start by saying not G bar, so that if G bar is a 0, it becomes inverted. And this half of my expression is a 1, so we'll have 1 ANDed with whatever comes next. Then I'm going to set up some Boolean logic to describe the output of the mux based on A and B. So using the truth table and those logic expressions that we wrote in the truth table, we're going to put that into our code right here. So I'm going to start a parentheses and then I'm going to indent so we can clearly see what's going on. So I know that if A and B are both low, C0 should pass. Here's our Boolean expression to represent that. Or if A is a 0 and B is a 1, C1 should pass. Or if A is a 1 and B is a 0, C2 should pass. Or if A and B are both 1, C3 will pass. That's going to sort of close up the parentheses that I started right here. So a lot of times we like to use extra space and indentation to show when something opens and closes, so we can be sure we didn't miss any parentheses. And that's going to be our data flow, or our Boolean representation of this multiplexer. So I'm going to go ahead and save it and check for errors. And so our symbol creation was successful, so we have no syntax errors. So this code is going to represent the operation of that 4 to 1 mux. This is one way to implement it. Notice that I had 4 inputs here. I could have used an array. Instead of 4 separate signals, I could have used standard logic vector to describe the input. So I'm actually going to modify this, showing you how that would look instead. So instead of C0, C1, C2, and C3, I'm just going to call the input C. And then I'm going to call it a type standard logic vector and give it a size. Since I have 4 elements or 4 inputs to my multiplexer, I'm going to make it a size of 3 down to 0. Now I've changed C, so right now if I were to try to create the symbol file for this, I'd get a bunch of errors because the compiler doesn't know what C0, C1, C2, or C3 are anymore. I've taken that away. What I'm going to do is update this so that I'm referencing a particular index within my array. So this would be cell 0. This would be cell 1. This would be cell 2. And this would be cell 3. Remember that because we define this as 3 down to 0, C3 is your most significant bit. C3 is the one that should pass if A and B are both 1, and then you go down the array from there. So now we've updated this to reflect an array. And I can go ahead and update the symbol file for this. It won't change what the symbol looks like on the outside. It just changes how the symbol operates on the inside using an array for those inputs. So that's 2 different ways you could start out to design your multiplexer. Next, I'm going to show you how to implement this multiplexer using something other than Boolean statements. Another part of the Dataflow style is something called a select expression. So I'm going to show you how that would work instead of these Boolean statements within our architecture. So I'm going to start by deleting all of this. Right here. And now I'm going to show you the syntax of a select expression. So we start with the keyword with. We have standard, logic, vector, and apostrophe, G bar, A, B, select. So this statement right here is going to take G bar, A, and B and combine them into a standard logic vector type. It's going to combine all of them together into a standard logic vector type. And what we're going to do then is hit enter, y gets C0 when 0, 0, 0, and we're going to type that all in quotes. Okay, so here's what this means. After the word when, this 0, 0, 0 represents the standard logic vector that was created with this statement right here. It's sort of like typecasting. You're taking things that were just standard logic and combining them into a vector. So this vector that we've created is G bar, A, and B in that order. So output Y is going to get C0, this input from this array, when G bar is a 0, A is a 0, and B is a 0. That's how a select statement works. And we're going to basically outline each option. Okay, so it's going to get C0 when this happens within the vector we've created. Okay, or it should get C1 when our vector equals 0, 0, 1. So when G bar is low and A is low and B is 1, the output should be C1. Or the output should be C2 when our vector is 0, 1, 0. When G bar is low, when A is a 1, and when B is a 0, the output should be C2. Or the output should be C3 when our input is 0, 1, 1. And we end the statement with what should happen if none of these things happen. Now, in a perfect world, one of these 4 scenarios is going to happen. But if none of these happen, you have to give what's called a default assignment. So the output will be 0 whenever G bar, A, and B do not fit any of these cases you've identified here. Okay. So, for example, if G bar is high, it's not enabled at that point. What do you want to happen when the device is not enabled? Well, we're saying output is 0. So anytime your vector that was created here doesn't fall into any one of these scenarios, your default assignment is what's going to happen. That's how you end your select statement, by indicating that default assignment. So this has no Boolean logic operators. We don't have and or not. We have none of that. This is a select statement. And so what the output will be selected from one of these choices based off of the values of G bar, A, and B. So I'm going to make sure that I don't have any errors. And we're successful. So that's how a select statement works. It's another alternative to using Boolean logic in the Dataflow style. Another tool that we can use in the Dataflow style is a conditional assignment statement. And in order to do that, we are going to implement a decoder, and then I'll show you how that statement works. So just to remind you what a 3-to-1 decoder would look like, here's a 3-to-1 decoder. You have 3 inputs, you have 8 outputs, and down here we have G1, G2A bar, G2B bar. Notice the names indicate whether these select inputs are active high or active low. So G1 has to be high, G2A bar has to be low, and G2B bar has to be low to enable the decoder. And then let's say that your input was CBA being 110. That'll select Y6 as the active output. The active output is selected based off of your inputs here, as well as whether the decoder is enabled. So Y6 will be your active output. Now remember, active doesn't necessarily mean high. This decoder has active low outputs. So normally these outputs are high. When an output is active, it will go low. It will go low. So as we implement our code, these are all things we have to keep in mind in order to implement the code successfully. So these are some of the requirements of our 3-to-1 decoder. So we're going to write the code for this, and I'm going to show you how to use a conditional signal assignment statement in order to implement the logic. So I'm going to go back to Quartus, and I'm just going to add a new VHDL file to my current project. And I'm going to start my new file with my context clause. And I'm going to call this entity decoder 328. Now, for our port statement, we've got to rely on the inputs and outputs that were defined in the diagram given. So our inputs were C, B, A. We also have our enables, G1, G2A bar, G2B bar. We had our output Y, which I'm going to define as a vector. With a size of 8. So there's my entity declaration for this decoder. We have our inputs, C, B, and A, which are in standard logic. We have G1, G2A bar, G2B bar, which are inputs standard logic. And then we have our output Y, standard logic vector, 7 down to 0. Now let's do our architecture. And we're going to be using that conditional signal assignment statement. So to begin our architecture, we're going to define a local signal. That signal is called enables. We're also going to have a second signal called CBA. They're both going to be standard logic vector. And I'm creating these specifically because I want to create what's called an aggregate, meaning I want to take these single inputs and aggregate them into an array. So I'll show you what that looks like. Enables gets G1, G2 A bar, G2B bar. CBA gets C, B, and A. If you're wondering, why didn't I just create vectors in the beginning to refer to these things? Because I also have a specific use or purpose for each individual element within the vector. I still want this first element to be known as G1, not cell 0 in a particular vector. It's very easy to create this vector called enables in your port statement and then forget, wait, which enable is G2 bar, which enable is G2 A bar, which enable is G2 B bar, which enable was G1. So by defining them individually in your port statement and then combining them into an aggregate array later allows you to keep straight what's what as you manipulate these three values. An array is great for storing lots of data, but your individual pieces of data is easily to lose track of what's what, especially when it's important to know which one is an active low versus which one is an active high. So I'm going to define them individually up here so that it's easier to keep track of what's what as I go throughout my code. But now enables is a local signal, so that's a local array, which is going to have these values, G1, G2 A bar, G2 B bar, in that order. CBA is also now a local signal that is a vector that has the value CBA in that order. Creating these here makes referring to them easier within my architecture, but if you think about this architecture, or rather, if you think about this entity being used as a part of a much larger system, I may need to know exactly what G2A bar is without the other variables, without having it lost or hidden within an array. So my symbol for this decoder is going to have these separate to make it easier to connect G2A bar, G2B bar, or G1 to something else in a much larger system. But within the context of the architecture, I can combine all of these into an aggregate. I can combine all of these into an array to make it easier to reference them as I go throughout my code. So that's the reason why I've done this step. I'm going to say y gets, and I have I have 1, 1, 1, 1, 1, 1, 1, 0. When enables is 1, 0, 0, and CBA equals. So what I'm saying is my output is going to be this, meaning the Y0 output is active when my enables are all enable. So G1 is high, G2A bar is low, G2B bar is low, and my CBA input is 0, 0, 0. So think about that decoder. If I put in 0, 0, 0, output 0 is the one that should be active. In this case, it's active low. So when I'm enabled and when the input is 0, 0, 0, Y0 is the output that is active while all the others are inactive. And this is a conditional signal assignment statement. That's what this is right here. Conditional signal assignment statement. So my output is this when, and then after the word when all of this is true, when everything after the word when is true, this value is assigned to the output. So I obviously have more cases here. I need to cover basically all of my inputs for when C, B, and A change. So I'm going to continue this statement by saying else. So what if this statement isn't true? If that's not true, I have to define what else should happen. So I have an else statement, and I'm going to have 1, 1, 1, 1, 1. Just copy it in here to make sure I don't miss any ones. Okay, so there's my what should happen next. So basically, when enables is 1, 0, 0, and CBA is 0, 0, 1. Now output 1 should be active, which is right there. Else, so I'm going to basically have 8 lines here where I talk about, or I discuss within my code, what should happen for each input value of C, B, and A, as long as it's enabled. So I'm just going to go ahead and copy this line, paste it, so I know that the next output should become enabled when CBA is 0, 1, 0. Now I'm just going to continue working through all possible options of CBA and changing which output will be active based on the value of CBA. So when C, B, and A is 0, 1, 1, output 3 should be inactive. It should be active. So this is output 0, output 1, output 2, and there's output 3. So this is going to allow output 4 to be active whenever the input is 1, 0, 0. Here's output 5 whenever the input is basically the decimal equivalent, which is 5. Output 6 is active whenever the inputs give you the decimal value for 6. And output 7 is active when the inputs give you 1, 1, 1. Right? We still need to give that default assignment. What if none of these happen? For example, what if it's not enabled? What should the output be then? So we're going to say this is our default assignment. That's our default assignment. So if it's not enabled, none of these conditions are happening. If it's not enabled, so we have to give that default assignment. What should happen if none of these things happen? Once we're done, we can end our architecture. And that's going to implement our 3 to 8 decoder. Notice that this is really one long statement. It's on several lines, but the semicolon doesn't appear till here. So it's really one long statement. Y is going to be this value when these things happen, else Y will be this value when these things happen, and so forth. That's a conditional signal assignment statement. Let's go ahead and save this. And check for errors. All right, let's go to line 19 and see what did we miss. I'll give you a second to look at it and see if you can figure it out. All right, so I've given you a second to look at it. Hopefully you can see it. Here's what's missing. An equal sign right there. Notice that we had an equal sign for CBA, but didn't have an equal sign here. Easy mistake to make. Again, I'm putting in mistakes hoping that you're learning how to catch them or how to figure out where the error is based off of the messages that you get down here. So now that we have fixed that error, we're going to save and run our symbol file again, and no errors. So this is our conditional signal assignment statement. This is how we can use something other than straight Boolean logic in order to design a system or a component in the Dataflow style. Another thing to add to this is if we have a situation where there's a don't care, like let's say that for whatever reason we don't care what G2B bar is. Instead of setting this up so that we say when enables equals 100, I can replace what I don't care about with a hyphen. So if you have a situation where you have don't care, so maybe you don't care about a third input, it's just something that doesn't matter for that particular section of your code, a don't care can be represented with the hyphen. All right, so that sort of sums up some of the other things that you can do with the Dataflow style besides write Boolean expressions. Depending on your application, a conditional signal assignment statement might be easier to implement, might make more sense, or it might be simpler to just use Boolean equations. It's really up to you. and what you're trying to accomplish and what you consider to be the most efficient. So that sort of wraps up our discussion on the data flow style. Next, we'll be discussing the behavioral flow style and how you can implement looping and if statements within your code. As always, you can email me if you have any questions, and that is the end of this video.